fighter jet is rarely ruined by enemy fire. It is usually ruined by desperate engineers trying to fix a fatal flaw. When the original Mikoyan-Gurevich MiG-29 first ripped through the skies in 1977, it was widely considered one of the most aerodynamically beautiful machines ever forged in metal. It was an apex predator designed for a single, brutal purpose. It was built to take off from shattered, debris-covered runways near the front lines of a hypothetical European war, rapidly climb into the freezing stratosphere, and slaughter incoming strike aircraft using its devastating maneuverability. But this aggressive knife-fighting design harbored a crippling secret. The baseline MiG-29 was notoriously, embarrassingly short-legged. It drank fuel at an apocalyptic rate, giving it an operational combat radius so small that pilots joked it could barely cross the runway without a refueler. If an engagement did not happen exactly where Soviet ground controllers predicted it would, the pilot would find himself staring at a glaring fuel warning light before the dogfight even began. For the Soviet Union, this was an acceptable compromise. They had tens of thousands of ground radar stations and rigid, tightly controlled combat doctrines. They did not need their light fighters to loiter for hours. They just needed them to intercept, kill, and immediately return to base. Then the Soviet Union collapsed, and suddenly the defense budget evaporated. The modern Russian state could no longer afford to maintain highly specialized, single-role interceptor fleets. War was changing. The West was showing off the multi-role dominance of fighters like the F-16 Fighting Falcon and the F/A-18 Hornet, jets that could shoot down rival aircraft in the morning and precisely destroy bridges in the afternoon. Russia needed a multi-role workhorse, but they had absolutely no money to design a new airframe from scratch. The Mikoyan-Gurevich Design Bureau was starving for cash, rapidly losing ground to their bitter rivals at Sukhoi, who were successfully exporting the massive, long-range Su-27 flanker to anyone with hard currency. If the MiG Design Bureau was going to survive the harsh economic winter of the 1990s, they had to prove the legendary Fulcrum could be modernized. They had to give it extreme range, precision ground strike capabilities, and modern avionics. They had to create the MiG-29SMT. And in doing so, they created what many aviation purists consider the ugliest upgrade in fighter history. Before we dive deep into exactly how this desperate engineering effort permanently altered the aerodynamics and combat legacy of the Fulcrum, I want to hear from you. If you are fascinated by the gritty, unpolished reality of military aviation and the engineering compromises that rarely make it onto the specification sheets, hit that subscribe button. We tear apart the myths of air combat here every week, and your support keeps these deep dive analyses coming. The engineers at Mikoyan faced an impossible mathematical problem. You cannot magically create internal volume inside an existing, tightly packed fighter jet. Every square centimeter of the original MiG-29 fuselage was already occupied by hydraulic lines, radar cooling systems, ammunition drums, and titanium structural frames. To solve the fuel crisis, they had to look outside the airframe. They decided to graft a massive, bulging conformal fuel tank directly onto the dorsal spine of the aircraft. This was not a subtle aerodynamic blister. It was an enormous, blocky structure that extended from the rear of the cockpit canopy all the way back to the twin vertical stabilizers. This grotesque addition earned the jet the immediate, unflattering nickname of the Hunchback or the Fatback. Aesthetically, it destroyed the sweeping, blended wing body lines of the original jet. But from an engineering standpoint, it was a blunt force triumph. That ugly hump held an extra 950 liters of aviation fuel. Combined with minor adjustments to the internal wing tanks, this modification finally pushed the combat radius of the fighter out to 1,000 kilometers without external drop tanks and over 2,100 kilometers when carrying 3 external tanks. For the first time in its life, the Fulcrum had the legs to actually hunt. But this raw fuel capacity came with a hidden operational cost that the aerodynamicists had warned about from the very beginning. Fighter jets are balanced on a razor-thin margin of center of gravity. When you strap nearly a metric ton of sloshing liquid fuel directly onto the upper spine of an aircraft, you fundamentally alter how that machine behaves in the air. The original Fulcrum was famous for its high angle of attack capabilities. It could point its nose aggressively, ignoring the traditional limits of aerodynamics thanks to the massive lift generated by its wide fuselage. The pilot could pull 9 Gs effortlessly, snapping the nose around to lock a heat-seeking missile onto an enemy. The MiG-29SMT, however, was a different beast entirely. With a full load of fuel in that spine tank, the jet became top-heavy. The center of gravity shifted rearward and upward. To prevent the aircraft from becoming completely uncontrollable, the engineers had to completely rewrite the flight control software. They implemented an advanced digital fly-by-wire system to artificially stabilize the jet, constantly making micro-adjustments to the control surfaces just to keep the nose pointed forward. When that spine tank was full, the pilot had to fight the weight. The roll rate decreased. The instantaneous turn rate, the very metric that made the original MiG famous, became sluggish. The aircraft felt heavy, unresponsive, and reluctant to maneuver. It was only after the pilot burned through the fuel in the dorsal tank that the jet slowly reverted to its old, agile self. But in modern combat, you do not always get to choose when the fight starts. If you are bounced by an enemy combat air patrol shortly after takeoff, you are forced to fight while flying a heavy, drag-inducing fuel truck. The aerodynamic penalty was just the beginning of the transformation. To make this jet a true multirole fighter, the engineers had to completely gut the cockpit and drag the avionics into the 21st century. If you look at the cockpit of a 1980s Soviet fighter, it is a chaotic, terrifying sea of turquoise metal and mechanical dials. It was designed under an entirely different philosophy of air combat. Soviet pilots were not expected to be autonomous hunters. They were considered biological extensions of the ground control interception network. The pilot stared at his instruments, listened to the ground controller in his headset, and flew exactly where he was told. The MiG-29SMT shattered that doctrine. The mechanical dials were aggressively ripped out. In their place, the engineers installed 2 large, full-color active matrix liquid crystal displays, measuring 6 by 8 inches each. These multifunction displays transformed the pilot from a blind pawn into a tactical manager. Suddenly, the pilot could pull up a digital moving map, overlay radar contacts, check weapon stores, and monitor engine health without darting his eyes around a cluttered dashboard. Furthermore, the engineers finally implemented a true hands-on throttle and stick system. In the high G stress of a dogfight, a pilot does not want to take his hands off the flight controls to flip a switch on the side console. It is distracting, dangerous, and burns precious seconds. The hands-on throttle and stick architecture allowed the pilot to cycle through radar modes, select different missiles, dispense flares, and lock onto targets using only the switches and hats located directly on the flight stick and the engine throttles. This fundamentally reduced the pilot workload. But all of these digital screens and switches were useless without a sensor to feed them data. The old N019 Rubin radar in the original Fulcrum was an analog nightmare. It was notoriously easily jammed, had terrible look-down, shoot-down performance, and absolutely no capability to map the ground. To turn the jet into a strike fighter, Mikoyan partnered with the Phasotron Radar Corporation to install the Zhuk ME radar. This was a massive leap forward. The Zhuk ME was a planar array radar that entirely changed the lethality of the aircraft. It could track up to 10 aerial targets simultaneously and provide continuous fire control solutions for 4 of them at once. It extended the head-on detection range of a fighter-sized target out to 120 kilometers. But the real magic of the Juk ME was its air-to-ground functionality. For the first time, a fulcrum could look at the dirt. The radar featured a synthetic aperture mapping mode. By bouncing radio waves off the terrain and analyzing the returning echoes, the radar could paint a highly detailed, black and white image of the battlefield below. A pilot flying at 20,000 feet could look at his digital screen and clearly identify a column of tanks, a bridge, or a fortified bunker from 80 kilometers away. This radar opened up an entirely new, devastating arsenal for the jet. The original fighter was limited to dumb bombs and unguided rockets. The MiG-29SMT, however, was wired for precision slaughter. It could now carry the KH-29T, a massive television-guided, air-to-surface missile capable of cracking reinforced concrete bunkers. It could drop KAB-500 laser-guided munitions with pinpoint accuracy. Perhaps most terrifyingly, it was integrated with the KH-31P anti-radiation missile. This changed the tactical geometry of the battlefield. The KH-31P is a supersonic, ramjet-powered missile designed specifically to hunt and destroy enemy air defense radars. A flight of MiG-29SMTs could now loiter at the edge of enemy airspace, wait for an enemy Patriot or Hawk battery to turn on its search radar, and fire a Mach 3 missile straight down the radar beam to obliterate the dish. On paper, the transformation was staggering. The Mikoyan engineers had taken a short-range, point-defense interceptor and hot-wired it into a heavy-hitting, long-range, multi-role strike platform. But the physical reality of building these machines revealed a very different story. You cannot add a massive fuel tank, heavy liquid crystal displays, new radar cooling pumps, and heavy air-to-ground missiles without paying a brutal price in physics. The empty weight of the MiG-29SMT skyrocketed. It was heavily burdened, deeply compromised, and structurally stressed. And this is where the engineers hit a wall they simply could not bypass. To push all of this new heavy metal through the sky, you need exceptional engines. The logical solution would have been to design an entirely new power plant. But again, the Russian defense industry in the late 1990s and early 2000s was starved of capital. They could not afford to invent a new engine. They were forced to rely on the Klimov RD-33 series 3 turbofan engines. These engines were absolute brutes. They pushed out over 18,300 pounds of thrust each when in full afterburner. They were rugged, they could ingest debris from rough runways without catastrophic failure, and they were reliable in freezing temperatures. But they were fundamentally a 1970s design, and they showed their age in two highly problematic ways. First, the thrust-to-weight ratio of the entire aircraft plummeted. The engines were simply not upgraded enough to seamlessly handle the massive weight penalty of the new airframe. The jet took longer to accelerate to supersonic speeds. Its energy retention during a sustained turn was significantly degraded. The pilot had to carefully manage his airspeed, knowing that if he bled off too much energy, the engines would take dangerously long to push the heavy jet back up to combat speed. Second, the RD-33 engines were notoriously, unabashedly smoky. Because of the design of their combustion chambers and fuel injection nozzles, they did not burn their fuel with perfect efficiency. At military power, without the afterburner engaged, the engines left a thick, dark trail of unburnt carbon particles trailing behind the jet. In the era of beyond visual range missile combat, you might think a smoke trail does not matter, but combat rarely goes exactly to plan. Missiles miss. Electronic warfare jams radars. Flights merge into the visual arena. And in a visual dogfight, a dark black smoke trail in the sky is an absolute death sentence. It allows an enemy pilot to spot you, track your energy state, and predict your exact flight path from miles away long before you can see him. The engineers tried to mitigate this with minor tweaks to the fuel flow, but they never truly solved it. The Hunchback fighter would always announce its presence to the naked eye. Despite these aerodynamic and propulsion compromises, the Russian government aggressively marketed the MiG-29SMT to the world. They desperately needed an export victory to keep the production lines running. And in 2006, they thought they had achieved their salvation. The Algerian Air Force signed a massive, highly lucrative contract to purchase 34 MiG-29SMT fighters, along with a handful of two-seat trainers for roughly $1.3 billion. This was supposed to be the triumphant return of the Mikoyan-Gurevich Corporation to the global stage. The first batch of 15 aircraft was delivered to Algeria in 2007. What followed was one of the most embarrassing and deeply damaging scandals in the history of the modern Russian defense industry. When the Algerian maintenance crews and aeronautical inspectors began tearing down the newly delivered jets for their initial acceptance checks, they were horrified by what they found. They expected factory-fresh, newly forged airframes. Instead, they found extensive corrosion on internal bulkheads. They discovered mismatched frayed wiring harnesses. They found substandard rusty components hidden deep inside the engine bays. The truth rapidly leaked out, and it was devastating. The Mikoyan Corporation, lacking the capital and the supply chain to quickly forge 34 completely new airframes from scratch, had taken a massive shortcut. They had scoured their storage yards and pulled out unsold, partially assembled MiG-29 airframes that had been sitting in the open air since the early 1990s. They had stripped the rust, slapped the new dorsal fuel tanks on the spine, installed the digital cockpits, painted them fresh, and tried to pass them off as brand new fighters. Algeria, infuriated by the deception, absolutely refused to accept the remaining aircraft. They halted all payments and demanded Russia take back the 15 jets that had already been delivered. The political fallout was catastrophic. The Russian government, desperate to save face and preserve their diplomatic relationship with a key North African ally, agreed to cancel the contract. The Russian state absorbed the financial blow, and in a move of pure bureaucratic desperation, the Russian Air Force was ordered to purchase all of the returned Algerian airframes. I want to pause here for a moment and ask you a direct question about this exact kind of military procurement disaster. When a country gets caught passing off 30-year-old rusty airframes as new, how long do you think it takes for their global defense export reputation to recover? Let me know your thoughts in the comments below, because the Algerian scandal fundamentally shifted the balance of power between MiG and Sukhoi for the next 2 decades. The Russian Air Force suddenly found themselves operating a fleet of MiG-29SMTs that they had never explicitly asked for and never truly wanted. They were forced to integrate these heavy, complicated, aerodynamically compromised jets into their frontline squadrons. And this is where the theoretical specifications on the brochure violently crashed into the gritty reality of Russian military logistics. Operating a highly digitized glass cockpit fighter requires an incredibly sophisticated maintenance infrastructure. You cannot just hand a wrench to a conscript and tell him to fix a faulty multifunction display. The maintenance crews despised the SMT. The massive dorsal fuel tank made accessing critical hydraulic lines and flight control actuators significantly more difficult. Routine inspections that used to take hours now took days because entire composite panels had to be carefully removed to reach the heavily packed internal architecture. The Phasotron Juke-ME radar, while highly capable on paper, proved to be temperamental in the field. It required extensive cooling, and its mean time between failures was noticeably shorter than the robust, simpler systems found on older Russian jets. If a radar processor failed, the entire aircraft was essentially grounded from its multirole mission until a highly specialized technician could replace the module. Furthermore, the airframe fatigue limits were a constant source of anxiety. The original MiG-29 was famous for its short service life. The Soviet philosophy dictated that fighters would be lost in combat long before they naturally wore out, so they were not built to last for 40 years. The engineers attempted to extend the structural lifespan of the SMT to 4,000 flight hours. But the added weight of the spine tank and heavy ground strike munitions subjected the airframe to extreme torsional stress during high-G maneuvers. Microcracks in the root of the vertical stabilizers became a known issue. The jets had to be flown carefully, their fatigue monitors constantly checked, destroying the illusion of a rugged, maintenance-free frontline fighter. The operational deployments of the aircraft only further highlighted its contradictions. When Russia intervened in the Syrian civil war in 2015, they eventually deployed a small detachment of MiG-29SMTs to Khmeimim Air Base in Latakia province. This was supposed to be the ultimate proving ground. The jet was finally going to fulfill its destiny as a precision strike fighter. The reality was far less glamorous. While the jets did fly hundreds of combat sorties, the Russian logistics chain struggled to supply a steady stream of expensive, precision-guided KAB-500 bombs or KH-29 missiles. More often than not, observers watched these highly upgraded, digitally advanced fighters taking off with their pylons loaded with cheap, unguided FAB-250 iron bombs. They were using a multi-million-dollar radar and advanced targeting computers to simply calculate the ballistic drop of dumb iron, diving toward the ground to release their unguided payload before immediately pulling away to avoid man-portable air defense systems. It was a stark demonstration of the difference between capability and capacity. The aircraft had the capability to wage a highly digitized precision war, but the military operating it lacked the logistical capacity to sustain that kind of war. The heavy, drag-inducing spine tank did exactly what it was designed to do. It allowed the jets to loiter over the Syrian desert longer than a baseline Fulcrum ever could. But it also meant they were slow to climb out of the target area, making them vulnerable to ground fire during the critical seconds after weapon release. Pilots operating out of the scorching heat of the Syrian air base also discovered that the environmental control systems in the cockpit struggled to keep the advanced avionics cool. The massive glass screens generated immense heat, and when parked on the tarmac in the blistering sun, the jets frequently suffered from software glitches and thermal shutdowns before they even reached the runway. Despite all of these flaws, these maintenance nightmares, and the humiliation of the Algerian rejection, the machine simply refused to die. It survived because it had to. It was an imperfect solution to a desperate problem. The Russian Air Force needed numbers to maintain their vast airspace, and the SMT provided those numbers at a fraction of the cost of buying brand-new Su-35 heavy fighters. But as the years dragged on, the ultimate tragedy of the MiG-29SMT became clear. It was a developmental dead end. The Mikoyan Design Bureau tried to use the lessons learned from the SMT to build an entirely new, flawless aircraft, the MiG-35. They attempted to take all the digital integration of the SMT, fix the aerodynamic drag by designing a better airframe, and install highly reliable thrust vectoring engines. But by the time the MiG-35 was ready, it was too late. The world had moved on. Stealth technology was dominating the conversation. The Russian government poured their limited resources into the Sukhoi Su-57 fifth-generation fighter program, effectively starving the MiG Corporation of its final chance at glory. The MiG-29SMT stands today as a harsh lesson in the limits of retrofitting. You can force new technology into an old shell. You can staple fuel tanks to a slender fuselage, rip out mechanical dials, and install brilliant planar array radars. But you can never completely escape the original DNA of the machine. The aircraft was born as a lightweight, agile interceptor designed to fight for 20 minutes over a dirt runway in Eastern Europe. forcing it to become a heavy, long-range bomb truck, destroyed the very aerodynamics that made it special in the first place, while never truly giving it the extreme range or payload capacity of a dedicated strike fighter like the Fe-15 Strike Eagle. It was a compromise written in titanium and aviation fuel. It kept the pilots flying. It kept the factories open just long enough to survive the dark days of the post-Soviet economic collapse, and it served its purpose as a heavily burdened bridge between the analog past and the digital future. It is ugly. It is heavy. It smokes. It handles poorly fully loaded, and its history is forever tainted by scandal and rusted bulkheads. But it flies. And in the brutal mathematics of global air power, sometimes an imperfect, heavy machine on the flight line is worth 10 perfect machines trapped on a blueprint. Thank you for diving into the messy, complicated, and utterly fascinating history of the MiG-29SMT with me today. If you want to keep exploring the absolute limits of aviation engineering and the raw truths of military hardware, make sure you are subscribed and hit the notification bell. Let me know in the comments which heavily compromised fighter jet you want me to tear apart next, and I will see you in the next analysis.